At the heart of every engine is a ring of 96 turbine blades that are the most amazing components in the whole engine. Jet engines work by sucking air into the core and through multiple compressors. Squashed to a 50th of its volume, this air is forced into a combustion chamber, where it explodes with fuel to create a ferocious gas jet. This jet is met head-on by the turbine blades, spinning them so fast that each blade delivers the same horsepower as a Formula One engine. The job these tiny blades have to do is unbelievably demanding.
The blade exists in a fairly harsh environment. It has to rotate at about 10,000 revolutions per minute, with a blade speed of about 800 miles per hour. The component itself operates at something like 300 degrees above the melting point of the alloy.
To operate at around 1700 degrees, they're designed not to melt.
Here you see the gas streams moving around the airfoil. At the bottom of the blade is the fir tree area, which is used to hold the blade into the disc. Above it you see the airfoils with a peppering of cooling holes.
To stop the blade melting, Rolls-Royce designers used computer modelling to design a blade that has a precise pattern of tiny air passages throughout.
Here we see what the blade would look like if we didn't have it cooled. And you can see that there are some areas of red, which means that the component is too hot. We put a cooling system inside of the blade, which cools it down to safe levels, and that cooling system takes away the same amount of energy that would boil a kettle in a 20th of a second.
But even with the cooling holes, no ordinary metal would be good enough. That's where the company's Materials Research Laboratory comes in, creating new metals with exactly the physical and chemical qualities demanded by the designers.
To try and achieve the properties that the designers want, we will design some trial compositions of alloys with different recipes, different blends of the alloy constituents, and then we will test those samples on different mechanical and environmental tests, and from that we'll choose the best possible blends which will deliver exactly the balance of properties that they require.
Using electron microscopes, the materials scientists can precisely analyse the microstructure of the alloy, checking that the crystal structure and mixture of metals is exactly as intended.
We've got a team of research specialists, about 25 in the team here in the UK, and there are teams in Germany and the States as well. And we're trying to draw on all the expertise that exists in the academic network around the world to bring all the best expertise we can into Rolls-Royce.
Even the finely balanced alloy recipe isn't the most advanced technology in the turbine blade. To cast the metal into its complex shape, a unique process is used, and it's another very closely guarded secret. It's done at a purpose-built foundry in Derby, where one of the few people who knows the secret is casting engineer Owen Draper.
If you take a normal piece of metal and solidify it from being molten, you'd end up with something that looks a bit like a granite worktop. Lots and lots of little different crystals, all in different directions. That's not very strong because the different crystals, the joins and the boundaries between them, they just cause a weakness. So what we aim to do here is to create a single crystal. Single crystal, no crystal boundaries, therefore it's an awful lot stronger.
The blade is made by growing a single crystal of metal into the correct shape. It's incredibly complex and demands a huge team of people working round the clock. But it starts with an intricate, hand-built model of the blade in skilled hands like Maureen Hankey's.
I've been doing it on and off since '73. Skill is you've got to be very dexterous, everything's got to be perfect, everything's got to be smooth.
The secret part is the way the molten metal is cooled through a spiral tube at the base of the mould. The tube prevents all but one crystal of solid metal from passing through, allowing that single crystal to grow throughout the mould. Imperfections could ruin the casting at any stage. Even the wax models are x-rayed by keen-eyed inspectors like Jackie Brown.
We were looking for defects in the core, i.e. cracks, chips, voids. When it's sentenced to scrap, is broken in half and put into the bin.
Once cast, every single blade is thoroughly checked, and checked again, by eye, by computer, and by X-ray. Even then, they're far from ready. Each blade goes through another 4 days of precision finishing in the hands of machinists like Steve Ball.
We're all very good at what we make. We don't sometimes share it. It's not until you see Trent Fleet fly over, I've made my own good bit of that.
And because of the extraordinary demands on the blade, its dimensions must be accurate to within 1/10 of a hair's width.
We grind the fir tree to within 7 microns, which is a hell of a tight limit. Goes under a load of 18 tons, that does. If we stretched it with 18 tons, re-gauged it, there would be nothing. Everything would be to the micron the same. There's no alterations in the structure. There's no cracking. There's no stretching of anything on there. And bearing in mind, you've got 96 of those in an engine set. Every one is like the first one. It's perfect. It's like a brand new baby. You treat it like that. That's why the focus of everybody in the shop's the same, whether it's 6 in the morning, 6 at night, 12 at night. Everybody's the same. The next one's always the most important, because all the rest are good. Because we've never had one come back. You can't argue with that.
It's the skills of people like Steve and the cutting-edge technology that keeps Trent engines ahead of the game. But innovation is a risky business. Designing the Trent engine almost brought Rolls-Royce to its knees.